Okay, so now we want to determine the irreducible representations the reducible representation is made of for the example of the BH3 molecule. So again, this is being given by the reduction formula applied to the point group, applied to the character table of the point group, which is D3H. So now in the point group D3H, we have overall 6 different irreducible representations, okay, associated with 6 different symmetry types, and we have to determine their numbers for each symmetry type. So we can, for instance, start with this first one, which is denoted A1 prime. And then the number of A1 primes would be 1 over the number of the 1 over the number of the symmetry operations in that point group, okay, which is 1 plus 2 plus 3 plus 1 plus 2 plus 3, and that gives overall 12. Okay, so it's 1 over 12. So now again we have to determine these products here for each symmetry operations. For each symmetry operation, we can, for instance, start with the identity operation. So for the identity operation, the number of operations in the class is 1. We have only 1 identity operation. We have to multiply this with the character of the reducible representation. So that is the one that we determined previously. And we can briefly go back so that we can see this. And we saw that this was actually 3, right? So that's 1 times 3. And then the character of the irreducible representation is this one here in the row for A1 prime underneath E, which is 1. So the first product is 1 times 3 times 1. All right. So the term for the next symmetry operation is the term for the C3 symmetry operations. So now the number of operations in the class is 2. Okay, because we have 2 C3 symmetry operations, the C3-1 and the C3-2, rotating around 120 and 240 degrees, respectively. So the character of the reducible representation, you can look this up, 0. And the character of the irreducible representation is now this one here, which is again 1. So the next term is the term for the C2 operations. So the number of operations in the class is now 3, because we have 3 C2 symmetry operations associated with the 3 C2 axes, 1 operation per axis, times the reducible representation, where the character for the reducible representation was 1, times the character of the irreducible representation, which is now this one here. Okay, so it's 3 times 1 times 1. So next we can look at the sigma h. So for the sigma h, the number of operations in the class is 1. The character of the reducible representation, well, that is 3, yeah, for sigma h. And the character of the irreducible representation is just this one here. Okay, so therefore we have 1 times 3 times 1. So now for the S3, the number of operations in the class is 2, because we have 2 S3. The character for the reducible representation, well, that is 0. And the character of the irreducible representation, this one here, is 1. So it is overall 2 times 0 times 1. So last but not least, we need to look at the sigma v. We have 3 sigma v's times 1, because the character of the reducible representation is 1, times 1, that is the character here in the irreducible representation for A1 prime underneath 3 sigma v. Okay, now that is just, when we calculate this, equal to 1. So that term here gives 12. 12 over 12, well, that gives 1. So that means that one of our ligand group orbitals has the symmetry type A1 prime. So again, we can do this the analogous calculation for the next symmetry type, which is A2 prime. And we would find that the number of irreducible representation is 0, and that means that no ligand group orbital has the symmetry type A2 prime. Okay. The next, we can go to E prime, which is shown here, and the result would be that the number of irreducible representations equal to 1. Okay. So that now means that 2 ligand group orbitals have the symmetry type E prime. So why 2 and not 1? That is because an E-type irreducible representation is a so-called doubly degenerate irreducible representation. That means that always occurs when 2 coordinates are actually dependent from each other, are actually transformed similarly by the symmetry operations in the particular point group. And in the point group D3H, it's the X and the Y axis in particular. And you can actually see this from the character table, because X and Y are listed both for the symmetry type E prime. Okay, now because of that double degeneracy, we know that despite the result 1 here, there are actually 2 ligand group orbitals of that symmetry type, and these 2 ligand group orbitals are doubly degenerate in the respective point group. Okay, so now we have found all our 3 ligand group orbitals that we have been looking for. The first one has the symmetry type A1 prime, and the other 2 have the symmetry type E prime. Now we know that there cannot be more than 3, so for that reason we actually do not have to do the explicit calculations for the remaining symmetry type, A1 prime prime, A2 prime prime, and E prime prime in particular. Okay, instead of that, we can go to the next step and combine the ligand group orbitals with atomic orbitals of the same time to form molecular orbitals. So before we do that, I wanted to discuss, though briefly, how we can understand the double degeneracy of the 2 ligand group orbitals. We can understand that using a so-called Walsh diagram. So in a Walsh diagram, you actually plot the ligand group orbitals and the energy in particular relative to a assumed bonding angle between the ligand group orbitals. So the largest bond angle that you can imagine between three hydrogen atoms having one s orbital each is a 180-degree bond angle. Okay, then you can actually assume three ligand group orbitals of different bonding characters. You can assume that, well, there will be one with zero nodes, and you would assume that all the amplitudes of the ligand of the 1s orbit are being the same. That would lead to a completely bonding situation. You can assume a second one having one node, okay? And in this one, only the first and the third 1s orbital would have an amplitude, and these amplitudes would be of opposite algebraic sign. The second one would have no amplitude, or we can also say the coefficient in front of that second 1s orbital is equal to 0. Then the respective orbital has one node. So we can characterize that orbital to be non-bonding, approximately non-bonding. So while we actually have a node, that orbital and that orbital are so far apart so that there's practically no orbital overlap, interbonding orbital overlap, rendering the entire orbital essentially non-bonding. So last but not least, we can actually flip the algebraic signs of the 1s orbitals so that they alternate. Okay, so the first one would be positive, the second one would be negative, and the third one would be positive. So that would create two nodes, and that orbital would obviously be interbonding. So now I can look at what will actually happen to the bonding nature, bonding or interbonding nature of these orbitals as we decrease the angle between the three hydrogens. Okay, so now the smallest angle that I actually can create is a 60-degree angle, and then I have essentially formed a triangle, and that is the geometric arrangement of the three hydrogen atoms within the BH3 molecule. You see that in the BH3 molecule, these three hydrogen atoms essentially form a triangle. Now, what will happen to the bonding character of the three orbitals that we discussed as we systematically decrease the angle from 180 degrees to 60 degrees? So now let us look at this orbital here first. So you can see that in addition to the bonding interactions here and here, as we decrease the bond angle, we also create bonding interactions between the first and the third orbital, okay, because we form a regular triangle. So we can say overall we have more bonding interactions, and for that reason this orbital becomes even more bonding. We can say it becomes strongly bonding in comparison to just bonding. So now for this one here, we see that as we decrease the bond angle, we are creating significant interactions between these two interbonding 1s orbitals. Okay, so we're actually creating this arrangement of orbitals here, where now these two that have interbonding overlap are closer together. For that reason, the overall bonding character changes from non-bonding to weakly interbonding. Okay, so now for this orbital here, we see that as we decrease the angle, these two orbitals come closer together. They have the same algebraic sign, and we are actually creating bonding interactions. Okay, so these interbonding interactions here and here remain, but now we also have some bonding interactions. So overall, the anti-bonding interactions are still more significant than the bonding interactions, but overall, we changed the bonding character of this orbital from anti-bonding to just weakly anti-bonding. And in fact, by calculation, one can show that these two cases here, this one and that one, are energetically exactly equivalent. Okay? So we can say that these two orbitals are degenerate relative to energy. Okay? And when they are degenerate relative to energy, they are also degenerate to symmetry. So these two orbitals here are actually the two ligand group orbitals that have the E prime symmetry type. This one here is the ligand group orbital which has the A1 prime symmetry type. Okay, so this should give you an understanding what degeneracy of orbitals mean. One useful property of group theory is that we know that when two orbitals are symmetrically degenerate, they're also energetically degenerate. Okay, and we can apply this knowledge when we construct the molecular orbital diagram. All right, now let's go to the next step and ask, well, what are the symmetry types of our central atom orbitals? We can see this directly from the character table. So the Born will have its 2s orbital. So the 2s orbital is always totally symmetric, and as an s orbital is in general. So it always has the symmetry type which is associated with the characters being equal to 1 in the respective irreducible representation. And that means that the 2s orbital has the symmetry type A1 prime. So now, what about the 2pz? So the 2pz will have the symmetry type A2 prime prime. As you can see from the character table, the letter Z here is listed in the irreducible representation of this symmetry type A2 prime prime. Okay, now what about the 2px? Okay, this one here. Well, you see the letter X is here in the row for the symmetry type E prime, and that means that the 2px must be doubly degenerate with another orbital, and that other orbital is the 2py, this one here, which is listed in the same row. Okay, so the character table tells you here that the 2px and the 2py orbital are doubly degenerate in the point group D3H. Okay, so now we can combine ligand group orbitals and central atom orbitals of the same symmetry type. So we determined that the 2s orbital has A1 prime symmetry, and that the three 1s orbitals have the same symmetry type for this ligand group orbital here. So that means you would expect one bonding and one anti-bonding molecular orbital of the symmetry type A1 prime. Okay. So now we also know that we have two ligand group orbitals with the symmetry type E prime and two central atom orbitals, namely the 2px and the 2py, having the symmetry type E prime. So now overall we are combining 4 orbitals. That means that we would expect 4 molecular orbitals with E prime symmetry. So now, because double degeneracy with respect to symmetry translates to double degeneracy with respect to energy, we know that two of the E prime orbitals must have the same energy and are bonding, and there are two other E prime molecular orbitals that have the same energy and are interbonding, and we must draw them accordingly into the molecular orbital diagram. Okay, so this is now shown here. We have here again on the left-hand side our atomic orbitals, and here on the right-hand side we have our ligand group orbitals. Okay, we know that we can combine the 2s with ligand group orbital 1. Okay, so that gives a bonding molecular orbital of that symmetry and an interbonding molecular orbital of that symmetry. Okay, and then we combine the 2px and 2py with LgO2 and LgO3, so that gives two bonding doubly degenerate orbitals and two interbonding doubly degenerate orbitals. Okay, so now what about the 2pz? So the 2pz does not find a partner. Okay, it has the symmetry type A2 prime prime, remember that, but no ligand group orbital has the symmetry type A2 prime prime. Okay, and therefore you can write it as a non-bonding orbital with the same energy into the molecular orbital diagram. So finally, you still need to fill in the electrons. So how many electrons do we have overall? Well, the boron has 3, and the hydrogens also have 3 overall, because we have 3 hydrogens, so that gives 6. So we fill these 6 electrons into the molecular orbitals according to energy. So that fills this one here. That fills these 2 here. Okay. So now you see that all the bonding molecular orbitals are being filled. No non-bonding and no interbonding orbitals are being filled, explaining the stability of the molecule. So we have overall 3 bonding molecular orbitals with which we can explain the 3 BH bonds. That would be the valence orbital picture. You see again that the molecular orbital picture gives you a refined view on the bonding situation in the BH3 orbital. In the valence bond picture, all the 6 electrons appear equivalent, representing the 3 BH bonds. In the molecular orbital picture, you can see differences. You see that these 4 electrons here are energetically actually not the same as these 2 electrons. Okay. All right. So now this was the brief review over molecular orbital theory. I'm doing this in more detail in my other course, Advanced Inorganic Chemistry. So what I want to emphasize here as part of this course is the extension of molecular orbital theory to band theory, which can now be applied to extended solids. So let us now go from molecular orbital theory to band theory. Okay, in our approach, let us consider the following. Let us assume that we have cycles of hydrogen atoms, regular cycles of hydrogen atoms, whereby we systematically increase the number of hydrogen atoms in these cycles And let us look at what are the respective molecular orbitals that result. Okay, so let us start with two hydrogen atoms that we combine to form a hydrogen H2 molecule. Okay, so now as we combine the two 1s orbitals of the hydrogen atom, well, we will form a bonding molecular orbital and an interbonding molecular orbital. So the bonding molecular orbital won't have a node. The interbonding molecular orbital will have a node, and therefore the interbonding molecular orbital has a higher energy. So now let's go from 2 to 3 hydrogen atoms and arrange them in a regular cycle. And that gives a triangle. Now, in this triangle, we would have one bonding molecular orbital in which we have no node, and two somewhat interbonding molecular orbitals which are doubly degenerate. So these interbonding molecular orbitals are actually the same that we already previously saw as ligand group orbitals in the BH3 molecule. Okay, you see them again here, okay, and here respectively. Okay, we understand now also why these are double degenerate, despite them looking very differently. All right, we can go from 3 to 4 members. Then we have a square. So now the molecular orbitals for this square would be this one here, which would be completely bonding and has no node. Okay. Then these two, which are doubly degenerate and have one node each. Okay. You see that the nodes are in somewhat different positions. Okay. So for this one, the node is actually horizontally, and for the other one, the node is vertically. But you can very easily see here from inspection that the bonding and interbonding interactions in that molecular orbital cancel out, and we have essentially a non-bonding orbital for both of them. So we have overall two non-bonding orbitals. So yeah, then we can increase the number of nodes even further. So that leads us to this molecular orbital here, which has then the highest energy. Okay, so now you can continue doing that and go from 4 members to 5 members to 6 members and eventually to an infinite number of hydrogen atoms, giving a circle. So now if you do this, then you will realize the following. You will realize that the energy differences between the molecular orbitals will become smaller and smaller. Okay, but the energy difference are not equal throughout. Okay, toward the more bonding orbitals, they become smaller, and as we go toward the more interbonding orbitals in this direction, they also become smaller. Okay, but overall, the energy differences between the orbitals are so small, so that we can say now that we actually have a band of molecular orbitals. Okay, with near infinitely small energy differences between the molecular orbitals. Okay, so now we've actually made the transition between molecular orbital theory and band theory. All right, so now what does that circle of hydrogen atoms have to do with the structure that we see in an extended solid? Okay, in an extended solid, we have always a periodic structure in a particular dimension. So now in one dimension, we have, well, 180-degree angle between the atoms. In the most simple case, the atoms would be hydrogen atoms. Okay, so you see that actually here. So if we just line up hydrogen atoms in a periodic fashion in one dimension, that becomes an infinite hydrogen chain. Okay, and the angle between three hydrogen atoms, an HHH angle, is 180 degrees. Now, this infinite circle is an approximation of an infinite hydrogen chain in the sense that when we have an infinite number of hydrogen atoms in that circle, then the bond angle between three hydrogen is practically 180 degrees also. Okay, it approaches 180 degrees. So therefore we can say that a circle of hydrogen atoms, assuming that we have an infinite number of hydrogen atoms, is equivalent to an infinite chain of hydrogen atoms that extends in a particular dimension. Okay, now if that is so, then also the a band associated with an infinite hydrogen chain of 1s orbitals should be equivalent to that band of a circle of hydrogen atoms containing an infinite number of hydrogen atoms. All right, now the most bonding orbital would again have no nodes, and the most anti-bonding orbital would have now the maximum number of possible nodes. So in this chain, we would alternate the algebraic sign of the 1s orbitals, thereby maximizing the number of nodes, and that would be the orbital with the highest energy. Okay, so now as we make the transition from molecular orbital to molecular orbital theory to band theory, we do not call the individual orbitals molecular orbitals anymore. We call them actually crystal orbitals. Okay, so this here would be the crystal orbital with the lowest energy and the lowest number of nodes, and this one here would be the crystal orbital with the highest energy and the greatest number of nodes. So now the question is, how can we describe the crystal orbitals in our crystal, which is, in our case, the one-dimensional hydrogen chain. Okay, so the one-dimensional hydrogen chain can also be considered to be the most simple crystal possible. Okay, there's only one dimension, and we have only 1s orbitals to consider. So now the crystal orbitals in that one-dimensional infinite hydrogen chain can be described by a Bloch function, and the Bloch function is given here. So it says that a single crystal orbital, which is a function of quantum number k, and I'm talking about that in a few moments, is equal to, well, the Euler number E times I times, well, K times N, whereby N is an integer number, times the lattice parameter A, which is nothing else but the distance between the hydrogen atoms in the one-dimensional hydrogen chain. So times the base function for the crystal orbitals, which is nothing else but the 1s orbitals of the individual hydrogen atoms. Okay. So now when we sum over all the hydrogen atoms in our one-dimensional infinite hydrogen chain, then we describe all the crystal orbitals in the overall band. All right, so now I mentioned the wave vector k is a quantum number. Actually, this wave vector k is a quantum number in the reciprocal space, and we can understand this, the following, by considering that k is equal to 2 pi over the wavelength of our crystal orbital. Okay, and now you see that the wavelength is in the denominator. Okay, so the wavelength is certainly associated with a length, and therefore k has actually the dimension of 1 over a length. Okay, and therefore we can say that k is has the unit of 1 over a length, and therefore it's a number in the reciprocal space. Okay, so now what do we mean by the wavelength of our crystal orbital? We can understand this when we again consider that we alternate the algebraic signs in the wave function of the crystal orbitals in a systematic way. Okay, so in this case here, we do not vary it at all. Okay, and therefore this crystal orbital would be associated with the crystal orbital of the largest wavelength. Okay, so the wavelength would actually be 2 times the lattice parameter times the number of the 1s orbital in the chain. Okay, and here you have the opposite case. So here the algebraic sign changes with every 1s orbital. Okay, and that crystal orbital would therefore have the shortest possible wavelength of all our crystal orbitals. So now overall, we can say that the wavelength is given by 2 times a times n over n. Okay, the shortest wave, for the shortest wavelength, lambda would just be 2a. In this case, n would be equal to n. Okay, and the longest, for the longest wavelength, n would be equal to 1. All right, whereby n just numbers the well, orbitals in our one-dimensional chain. All right. Now, knowing that, we can say that k is equal to n times pi times, over a times n, if you just substitute that lambda, by 2 times a times n over n. So now we can think about between which values k can actually vary. Okay. Now, one extreme case is that n is equal to n. And well, in this case, k would be equal to pi over a. So that is the greatest possible value k can adopt. Okay, so the smallest possible value is just 0 when n is equal to 0. Okay, so that means that all our crystal orbitals are associated with wave vectors k that can vary in value between 0 and pi over a. Okay, now we can calculate if that result actually makes sense. We can calculate the actual crystal orbitals for k equal to 0 and k equal to pi a respectively. Okay, so what we'll need to do is to insert k equal to 0 into that formula for the Bloch function, which gives us the crystal orbital. Okay, so now if we do this, then the result is that psi 0 is equal to, well, e to the power of 0, because k is equal to 0, times chi n. Okay, and this is just 1. Okay, so if we sum up over all the n's, over all the 1s orbitals that we can have, then basically our crystal orbital, the formula for our crystal orbital is chi 0 plus chi 1 plus chi 2 plus chi 3. All right, so this would refer to this picture here for the most bonding crystal orbital. So that means that at k equal to 0, we would find the most bonding crystal orbital. All right, now let's go to k is equal to pi over a. So in this case, psi pi over a would be equal to e to the power of pi times I times n. So that transforms to chi n is equal to the sum over minus n times the power of n. All right. So now it depends on n is equal to is even or odd. Okay. So when I take minus 1 times an even number, okay, it will be 1, and if I take it times an odd number, it will be minus 1. So therefore, chi n will be chi 0 minus chi 1 plus chi 2 minus chi 3, and so on. Or if you visualize that, it will represent 1s orbitals with opposite algebraic sign. So chi 0 will have a positive algebraic sign, the 1s orbital for chi1 will have a negative algebraic sign, the next one will be positive, the next one will be negative, and so forth. So you can easily see that this crystal orbital is the most interbonding crystal orbital possible, and we will find it at k equal to pi over a. So now we can plot the energy of our crystal orbitals versus k, whereby k can vary between 0 and pi over a. Okay, and you will find that the energy values adopt this kind of S-shaped curve. Okay, so at very low k values, the slope will be relatively small, then the slope will be maximum halfways, okay, and then the slope will again become smaller. So this is because, qualitatively spoken, because of this phenomenon here, the energy differences here in the non-bonding regions are smaller than the energy differences between the crystal orbits here in the most interbonding and the most bonding regions. So this translates to a relatively small slope near 0 and pi minus a, and a steep slope halfways between 0 and pi over a. So let us stop at this point. So this was my introduction into band theory. Let us now stop the recording